Radioactive decays. Only nuclei that lay along the black line of stability are stable. That is, they live forever. So along that black line. Looking at the band of stability, if nuclei live in the turquoise, the orange, or the yellow regions, they are unstable, and at some point in their lives, they will decay. Of all of these nuclei, 85% of unstable nuclei will emit radiation, where the most common radiation come in three distinct types. They're called alpha, beta, gamma. Let me make some remarks about these. These radiations were discovered by Rutherford and friends around 1900. Alpha, beta, and gamma are the first three letters of the Greek alphabet. Rutherford coined these terms by how much these radiations penetrated ordinary materials. Alpha penetrates the least distance and can be stopped by a sheet of paper. Beta penetrates several millimeter thick sheets of aluminum and therefore goes further into materials. Gamma must be stopped by lead bricks and therefore penetrates the furthest. Otherwise, if I sent an alpha and here was a sheet of paper, it would be stopped by the piece of paper. However, beta would go right through the paper, but a sheet of aluminum would stop beta, but gamma would continue to go through. You need a lead brick in order to stop gamma from going all the way through. Question: what is a radioactive decay? A radioactive decay is a nuclear process by which a nucleus spontaneously undergoes a change. That means either the number of protons change or there's a jump from a higher to a lower energy, and in that process, energy is emitted by the nuclei. Alpha and beta decays result in emission of particles from the nucleus. This means that with these decays, it changes the atomic number. Remember, the atomic number is the number of protons, but if it changes the atomic number, then this decay changes the type of atom that it started with. Gamma rays are a release of high-energy light waves, and we already talked about light waves when we were dealing with the quantum atom. These decays do not change the nuclei, and therefore the atom does not change, whereas alpha and beta do change the atom. Now I want to go through the three decays: alpha, beta, gamma. Alpha decays. Many large nuclei are unstable, starting with bismuth, which has an atomic number of 83. It is common for them to spontaneously break apart into smaller fragments. One particular fragment is a helium nuclei without its electrons, so that it's positively charged. Helium nuclei is an ion, a charged ion. It is this helium ion that it's called an alpha particle. There's a difference between a helium atom and an alpha particle. A helium atom is neutral. On the other hand, an alpha particle is positively charged. What does an alpha particle do to an unstable nuclei? Unstable nuclei goes through an alpha decay. It reduces the atomic mass by 4 and the atomic number by 2. Remember, an alpha particle is a helium nuclei. So you can see here's the 4 for the atomic mass, and here's the 2 for the atomic number. Alpha decays happen mostly for nuclei with atomic numbers equal to or greater than 83, which is bismuth. And now I want to sketch or picture of an alpha decay process of an unstable nuclei. In a large nuclei, in this case it's 238, uranium spontaneously decays by breaking into two smaller fragments. One of these fragments is almost always an alpha particle. Look at this example. I have a nuclei of 238 uranium. Now, the original nuclei is always called the parent nucleus. So if I calculate the numbers for uranium, I have 146 neutrons, 92 protons. Since uranium-238 is unstable, it spontaneously decays. So I'm trying to depict this by this little explosion type thing. Part of this process comes two fragments. One is an alpha particle. Remember, an alpha particle is a helium nuclei. But from now on, I'm going to start drawing this alpha particle with 4 and 2 with the symbol alpha. And then we have a daughter. So how do I get the details about the daughter here? In alpha decay, the alpha particle carries off an atomic mass of 4 and an atomic number of 2. So when I look at the uranium nuclei, the atomic mass of 146 is now reduced by 4, so it's 142, and the atomic number 92 gets reduced by 2, so now it's 90. Since all atoms are identified by their atomic number, the atomic number of 90 is thorium. I then write the nuclear reaction as 238 uranium, and then the arrow here indicates the spontaneous decay, and it goes into 142 thorium plus my alpha particle plus energy that I didn't depict here, but there's energy that's also released by the nuclei. Let's look at an everyday example of alpha decay. Americium-241 is radioactive since its atomic number is larger than 82. This artificial atom must be produced in nuclear reactors. The isotope is part of a sensing circuit in most smoke alarms, and when it decays, it emits alpha particles. Question: what is the daughter nucleus? We know that americium-241 decays via alpha, so when I look at americium-241, I know that the alpha is carrying 4 of the atomic mass and 2 of the atomic number. It means then that the daughter nuclei has to have 4 less of 241 and 2 less of 93. So the daughter nuclei has to have an atomic number of 93, but that's unique. So the atomic number is 93, which is neptunium, and so therefore it's this isotope of neptunium. So the way a smoke detector works here is that americium is constantly emitting alpha particles, and then there's a detector. If the detector stops sensing the incoming alpha particles, then the smoke alarm goes off. How you stop the alpha particles from hitting the detector is by smoke particles. They're big enough to actually stop the alphas. Beta decays. In beta decays, a nucleus spontaneously decays by emitting a beta particle. So this beta particle is the Greek symbol beta with the minus sign. But before they realized that the beta particle was an electron, they called it a beta. One very important beta decay is that of carbon-14. And what happens here is that carbon-14, when it decays, it goes to nitrogen-14, plus it emits a beta minus particle, plus extra energy coming out of the nuclei. So comparing these two nuclei, you could see that both of them have atomic masses of 14. In other words, the atomic mass does not change. On the other hand, if you look at the atomic number, it went from 6 to 7. So the atomic number increased by 1. So if we look at the details, carbon-14 has 8 neutrons, 6 protons. Nitrogen-14 has 7 neutrons, 7 protons. So when I look at the neutron number, we could see here that it decreased by 1, but on the other hand, the protons increased by 1. So in summary, it is a neutron that decays into a proton, emitting a beta minus particle and energy. This is the definition of a beta minus decay. Picture-wise, I have carbon-14 here. It has 8 neutrons, 6 protons. So the reds are the protons, the blue are the neutrons. So what I'm going to do here is that I'm going to focus on this green neutron. Now it spontaneously decays. What happens? That green neutron turns into this green proton, but simultaneously it emits a beta particle, a beta minus particle, and there's other energy that leaves the nuclei. To wrap this up, a neutron within the nucleus has changed itself into a proton, and in that process it emits a beta particle and extra energy from the nuclei. This type of decay usually happens to neutron-rich unstable nuclei. There's a related decay called inverse beta decay. In beta decay, a neutron turned into a proton. In inverse beta decay, a proton turns into a neutron, just the opposite case. So we see here that a proton goes to a neutron, plus it emits this beta plus particle and that energy, where this beta plus is called a positron, and a positron is a positive electron. One nuclear reaction of fluorine-18 is decaying via inverse beta decay. So I have fluorine-18 going to oxygen-18 plus emitting a beta plus particle and energy. But look at the following thing. The atomic masses for both of these are the same. The atomic mass does not change, just like regular beta decay. But this time, instead of the atomic number increasing by 1, the atomic number decreased by 1. Looking at the details for fluorine-18, I have 9 neutrons, 9 protons. For nitrogen-18, I have 10 neutrons, 8 protons. So you could see here that the number of neutrons increased by 1, the number of protons decreased by 1. That is inverse beta decay. Drawing a picture for this decay here, I'm going to focus on this green proton. So this green proton is then going to decay into this green neutron, and in this process it emits a positive beta particle and extra energy coming out of the nuclei. In summary, we can say the following. A proton within the nucleus has changed itself into a neutron by emitting an inverse beta particle, as well as energy. This type of decay usually happens to proton-rich unstable nuclei. Last of the common decays, gamma decays. When we studied the quantum atom, we learned light was emitted by the atom when an electron jumps from a higher energy level down to a lower energy level. So in this case, as it jumps from 3 to 1, it emitted radiation. That radiation is also called light. The nucleons of nuclei, remember nucleons or neutrons or protons, live in energy levels also, just like the electrons do in atoms. So if I have a nucleon that's in an excited state, and if it falls to this lower level, that nucleon will emit gamma radiation or a gamma ray, which is depicted by the Greek symbol gamma. In general, nuclei left to themselves are usually in their lowest possible state or level. That's what we call the ground state, and cannot emit gammas. However, alpha and beta decays often leave daughter nuclei in excited states, and you need an excited state in order to get gamma radiation. Because of this, gamma emission is often found to accompany alpha and beta decays. An important radioactive isotope for medical imaging, known as SPECT, is 99 technetium. We start with molybdenum 99, and it decays to technetium 99, but this time it's in an excited state. It's this excited state that's most important to this medical imaging. So then the excited technetium 99 decays to de-excited technetium 99 plus emission of this gamma ray. So when you look at the atomic masses of the excited state and the de-excited states, it does not change. If you look at the atomic numbers, it does not change also. It is this gamma ray that is used for medical imaging. Now let's draw a picture of the reaction. I start with molybdenum 99, which is in a higher energy state, and then it decays beta-wise. And as molybdenum decays, it now leaves technetium in an excited state after emitting that beta minus particle. And excited technetium then decays to a de-excited state, and it's this gamma ray that is emitted here. So this is an image of a false color gamma emission coming from the brain here. But that's exactly where that gamma ray is coming from to produce this image inside the brain. Radioactive decays and the band of stability. We revisit the band of stability and include radioactive decays this time to explain in more detail what happens to unstable nuclei. A key point of energy is that systems always move from a high to a low energy state. Now, if we apply this to nuclei, unstable nuclei, which represents higher energy states, always decay towards stable nuclei, which are lower energy states. Let's summarize what we talked about neutron-proton ratio numbers. Nuclei are most stable when their neutron to proton ratios, which I'm going to depict as N divided by P, which is equal to the number of neutrons divided by the number of protons, follow these basic observations. 1. Nuclei with atomic numbers less than 20 are most stable when their neutron-proton ratios are about 1. Nuclei with atomic numbers less than 20 are most stable when N over P is equal to 1. Symbolically, I'll write it this way. Nuclei with atomic numbers between 20 and 83 are most stable when for mid-weight nuclei, NP is approximately 1.2, while for heavy nuclei, NP is equal to 1.5. I'll write this as, so if the atomic number is between 20 and 83, these atoms are most stable when NP is approximately 1.2 for midweight nuclei, and N over P is approximately equal to 1.5. That's for heavy nuclei. There are 3 effective regions in the band of stability. In the turquoise region, which is this region right here, these nuclei are unstable because they either have too many neutrons or too few protons. In the orange region, and this orange region you could see goes along here. There's a tiny bit right here, but that's a little of an outlier. These nuclei are unstable because they have too many protons and too few neutrons. So you could see here that it's to the right or below the black line of stability, whereas the turquoise region is to the left and above the black line of stability. And then the last region is the yellow region, and you could see here that this yellow region is this area right in there. And this region is above the black line of stability. These nuclei are unstable because they have too many neutrons and protons, or they're too heavy. I'm now going to go through each of these sections. The turquoise region. For isotopes that land in the turquoise region, and I've highlighted here in this pink line, which is to the left of the black line of stability, they have too many neutrons to be stable. This means these nuclei must get rid of neutrons in order for them to become more stable. Remember, any nuclei that is unstable will decay and move towards the black line of stability. There is only one way possible to reduce neutrons: beta decays. In a beta decay, a neutron is converted into a proton, plus emitting a beta minus particle and energy. Unstable nuclei in this region have too high of a neutron to proton ratio. In other words, there's too many neutrons and too little protons. So what a beta minus decay does is it reduces the neutron to proton ratio and moving it closer to the black line of stability. Example: determine the neutron-proton ratio of carbon 12, 13, and 14 and identify the most stable state. Since carbon has an atomic number of 6, we could calculate the neutrons and protons and calculate their neutron-proton ratios. So for carbon 12, I have a ratio of 1, carbon 13, I have a ratio of 1.2, and carbon 14, I have a ratio of 1.3. From Wikipedia, I ended up getting the main isotopes of carbon, and when I look at these decays, the decay of carbon 14 occurs with a beta minus decay, and it goes to nitrogen 14. And we discussed this earlier. So what I've done here is I've cut off the corner of the band of stability, and now I want to look at these carbons. So each of these carbons have protons of 6. So that means that this here is the line of 6 protons right here. So when I go and I look at carbon 6, it has 6 neutrons. So right here is my 6 neutron line. Carbon 14 is up here on this line, and that's where I have the 8 neutrons. The carbon 13 with its 7 neutrons is right there, and it's hard to tell, but it actually lies on the black line of stability. So the only one that doesn't lie on the black line of stability here is this carbon 14. And how do I know that? Here are the main isotopes of carbon. Carbon 12 and 13 are stable, so they're on the black line of stability. But when you look at carbon 14, you could see that it's unstable, and its primary decay mode is nitrogen 14. That means carbon 14 decays through beta decay, where a neutron is converted into a proton. So it's reducing the number of neutrons up here and increasing the number of protons. And so when I calculate that ratio for neutrons to protons for nitrogen, I find that nitrogen has 7 neutrons, 7 protons, so its ratio N over P is then 1. So when you look at where this lands, it lands right there, and that's on the black line of stability. So carbon 14 decayed to a more stable nuclei. In summary, if an isotope falls to the left of the black line of stability, it contains too many neutrons or too few protons. Unstable nuclei will always go beta decay to decrease the number of neutrons and increase the number of protons to reach the black line of stability. The orange region, this region is right here. It's right to the right of the black line of stability. For isotopes that land in the orange region, which is to the right of the black line of stability, they have too few neutrons to be stable. This means these nuclei must get rid of protons in order to become stable. The only way possible to reduce protons is through inverse beta decay, where a proton is converted into a neutron and the emission of a beta plus and energy. So unstable nuclei in this region have too low of a neutron-proton ratio. So what beta plus does is it increases NP, and by doing this, they move upwards towards the black line of stability. Let's look at an inverse beta decay for isotopes of sodium. So from Wikipedia, I have sodium 22, 23, 24, and if you look at 22 here, it goes through a beta plus decay. So this is the one that we want to focus on. And you could see that its main decay product is neon 22. So according to this table, sodium 22 decays to neon 22 by inverse beta decay. I now calculate the number of proton ratios. So for sodium, I get 11 over 11, which is 1. For neon, I get 12 over 10, which is 1.2. So if I go to the band of stability, I still have this corner that I cut out. You could see that the black line of stability does not land on the line. That black line, that's where NP is equal to 1. But as this thing goes through an inverse beta decay, it shifts it to the left and up, which lands in the band of stability. So neon 22 is stable. So what you're seeing here is that there's a move from here to there. And that's what the inverse beta decay did. In summary, if an isotope falls to the right of the black line of stability, it contains too many protons or too few neutrons. Unstable nuclei will always go inverse beta decay to decrease the number of protons and increase the number of neutrons to reach that black line of stability. Yellow region, which is this region right in here. Now you could see that right in here, there's a little bit of yellow right in here. There's a little bit of orange. That's a little bit more complicated than what we really want to talk about. For heavy nuclei with atomic numbers greater than 82, these isotopes are too heavy and will alpha decay because emitting alpha particles is the quickest way to reduce mass. One example is thorium-232. It starts as an unstable nuclei and then it goes through a chain of decays where it finally lands to lead-208. Now these decay chains are complicated. Here's an image of one of these. So what you find here is that when you look at where it starts at this 232 thorium, which is in the yellow region, which is unstable. And the end product is this 208 lead, which is essentially the very last element on the black line of stability. So what it does then is it goes through a series of chain reactions. So you could see that thorium decays to radon, and then there's all these series of decays until it finally gets to lead here. So as I go from this spot to that spot, you're finding here that that's a long ways in this band of stability. So that's why it must have a series of chain of decays.